Good afternoon, guys. So today I have something new in store for us. Because my markers have all been dying, I've set up a document camera, and so I am going to see how this works. Hopefully, right now, what you're seeing is the image from this dot cam. It's my hand. This is a little bit awkward because of where things are positioned for me. So I'll ask that you bear with me as kind of I get used to this too. But I think it might provide a better system for us, at least while my markers are also crappy. So really quick, just in chat, can you let me know if you guys are seeing what you ought to be seeing? Okay, it looks good. You can see the paper. Everything is clear. No focus issues. No crowding issues. That is awesome. Oh, hang on one sec. Yeah, go ahead and do that. All right. Okay, so then today we're going to talk more about polar coordinates. And then if there's time, we're also going to introduce this idea of a parametric curve. So we're still in section 8.2. And we're going to stay here for a little bit. I think I might be, because I was nervous about getting this to work, might be still a little bit early, so I might want to wait just a second for some more folks to show up. Oh, no, we're right about on time. Okay, so I'll recap what we discovered last time, and then I will show you a few new graphs. There's some graphs we haven't seen yet. And then we'll just try to get a bit more practice. If there's time, then we'll talk about parametric curves towards the end. Your homework this week, I don't think I included anything on parametric curves. I think it's all just polar coordinate stuff. So aside from graphing the curves, which is nice and an important skill, of course, we also want to kind of develop a familiarity with families of curves. So last time, we saw that R equals, I was writing it like this, 2a cos theta, or R equals 2a sine theta. That these are circles when we graph them in polar coordinates. Of radius a. And maybe I'll call this R1 and this R2. R1, his circle is centered on the positive x-axis. If a is positive, or on the negative x-axis if a is negative, centered at the point a comma 0, and R2's circle is centered along the vertical axis. So he's centered at 0 comma a. And these are still, I would argue, nicer equations than the equation for a circle in Cartesian coordinates, which is like x minus h squared plus y minus k squared equals r squared. And if you want to solve that for y and make it look like it's a function, then the explicit expression for y involves this big square root of all sorts of quadratic terms. It's messy, whereas here, fairly simple stuff. We also saw that r equals a constant is a circle of radius C centered at the origin. And that theta equals C, these are rays, or that's usually the way we like to say it, emanating from the origin. You could also just think of them as lines through the origin, straight lines. So these are the families of polar curves that we should have a fairly decent understanding of at this point. And I want to start to stretch this out. We did look at cardioids. I don't think we looked at many cardioids. So let me see. I think last time we did 2 plus 2 cos theta, right? So we, yeah, maybe instead of marking this as a 3, then we saw it was this heart-shaped graph. So he looked more or less like this. Oh, move that up. So, and then we saw one other specific example. This one was a petal graph. Sometimes they're called petal graphs or flower graphs. Your book calls them rose graphs. I don't remember the exact example we did. Sine 2 theta? Or cos 2 theta, right? Yeah. And this guy's graph looked like this. So these last two guys are also members of larger families. And one of the things I would like to do today is to explore those families in a little bit more detail to come to a kind of general result akin to what we had for the circles. So these cardioids, equations that look like this cardioid's equation, 2 plus 2 cos theta, don't always yield exactly cardioids. We mentioned that if this guy was not a 2, or if, let's say, if this guy was a 1, so that this graph dipped below the x-axis, that would create some loopy behavior, kind of like in the petal graph. So that's what I'd like to look at next, and those are called limosons. So one example of another member of this sort of family of curves, even though it's not actually a cardioid, would be this next guy we're going to play around with, and he's called a limoson. I am going to run into a paper deficit here, but we'll work for a minute, and then I'll go grab paper as needed. So for our next little example, as we learn how to sketch in polar coordinates, I think it would be wise to look at something like r equals 1 plus 2 cos theta. And I'm going to do this not by making a table of values and then plotting the points and doing one at a time and connecting with a curve, but I want to go from the rectangular graph to the polar graph. So I want to graph this guy in rectangular coordinates like we did for the last 2 examples last time, and then transfer that graph over into polar coordinates. One of the big advantages of doing that is that you can see R increasing and you can see where R is decreasing. And that really helps with the intuition that's necessary to get comfy here. So we begin with the rectangular graph, or the rectangular coordinate graph. And remember, regardless of the period of this function, you always want to graph at least out to 2 pi. So I'll label my axes here. Let's see, what are we going to need? We're going to need a little bit more vertical space in that direction. One, 2, and 3. This is the theta axis, and I'm going to go out to at least 2 pi. I like to draw in the equilibrium. So the equilibrium for this guy, if the cosine term is 0, is the horizontal line r equals 1. So I like to put him in as a dashed line, makes it easier for me to draw these. And the amplitude of the cosine wave I'm going to draw here is 2. So we're going to start all the way up here at positive 3, and then we're going to come down, down, down until we get to negative 1. So I'm going to go ahead and put a tick in for negative 1. And I'll just start by putting in some of the more obvious points. So if this is 2 pi, then right here is pi. And by the time I get to pi, I need to be all the way down at my min, which is here. And then by the time I get to 2 pi, I need to be all the way back up at my max, which is here. So I know that this cosine wave is going to look something, and forgive my bad art, something like this. All right, so here's the rectangular coordinate graph of 1 plus 2 cos theta. It's a cosine wave with amplitude 2, shifted up 1. As always, we want to label all the important points, right? Quote unquote important points on this graph. That's anywhere you hit a min, a max, pass through equilibrium, or go through 0. So I'll label these equilibrium points. And I'm also going to label these x-intercepts. This is, of course, 0, 3. This is 2 pi, 3. And this is pi, negative 1. We'll worry about the x-intercepts in a minute. What is the x-coordinate, or sorry, theta coordinate of this point right here, that equilibrium point? Imagine this wasn't vertically shifted, right? Then that would be a horizontal intercept. Yeah, good, pi over 2. So this is pi over 2, 1. And this guy right here is 3 pi over 2, 1. To find the horizontal intercepts, we're going to have to solve an equation. Along this axis, if the vertical axis here is my r axis, then this is when r is equal to 0. So I need to solve 0 equals 1 plus 2 cos theta. And thankfully, that's not a difficult trig equation to solve. Subtract the 1 and divide by 2, and you'll see this is the same as saying -1/2 is equal to cos theta, which of course has infinitely many solutions, but I'm just looking for these two. I'm looking for the one that's between 0 and pi, and I'm looking for the one that's between pi and 2 pi. So where is cosine equal to -1/2? Well, cosine's that x-coordinate on the unit circle, so I have to rotate past pi over 2. And then how far past pi over 2 do I have to rotate? Oh, just a little bit, right? It's not the √3/2 one, it's the 1/2 one. So this first solution is 2 pi over 3. And then this second solution, so this right here is 2 pi over 3. The second guy is 4 pi over 3. And those are both just coming from thinking about my unit circle. So that's a really nice rectangular coordinate graph of this function that I can now transfer into polar coordinates. Before I start drawing the polar graph, are there any questions about where any of the features on this rectangular coordinate graph are coming from? So anytime you're asked to graph a polar function or graph a function in polar coordinates, this is always the procedure. Give yourself a nice graph in rectangular coordinates with all the good shit labeled, and then we'll slowly try to transfer it over into polar coordinates. So I'll give a little bit of space here. So some nice big axes. So this will be my polar graph. I know that when theta is equal to 0, r is equal to 3. So we're going to start at the polar point, r comma theta, 3 comma 0. So I need to take off some measurements here, call that 1, call that 2, call that 3 along my polar axis. And I begin here, the polar point, 3 comma 0. Now as as theta starts to rotate up, what is r doing? Is my little man walking in along that arm, or is he walking out along that arm? I see here that r is decreasing as theta starts to increase. So as theta goes up, this point is going to want to run in. I think the next explicit point to plot for us would be the pi over 2 comma 1's translated point. So as this arm rotates up, my little dude, this dot, is running in along the arm, and by the time I get to be facing like this at pi over 2, and theta is pi over 2, r has retreated from 3 down to 1. So I'll try to scale these similarly. So as I rotate, the dot runs in, and by the time I'm up here, the dot's already down all the way down to 1. So that's going to give me a curve something like this. All right, we come out of here vertically, and we go over like that. Now as theta rotates past pi over 2, r is still contracting, and it's coming in until we get to 2 pi over 3, where it comes into 0. So by the time my arm is like this, at 2 pi over 3, r needs to have run all the way into 0, which is going to draw for me something like that. And this curve here is tangent to the ray at 2 pi over 3. As theta goes past 2 pi over 3, as I continue to rotate beyond that, sorry, I know we're covering it up a little bit. Maybe I can get a smaller thing to rotate for you is that arm. All right, here, might look better. As this arm continues to rotate, once I go past 2 pi over 3 right here, something weird happens. R becomes negative. All right, as I come past 2 pi over 3, R becomes negative. So instead of drawing over here, where you think we would draw during that theta interval, we're actually going to be drawing at the reflected space over here. So this is what's going to generate that little inner loop that we talked about last time. So if I let theta rotate just a little bit past 2 pi over 3, if R was positive, I would want to start poking out and drawing like right in here. But since R is negative, I'm actually going to be poking out and drawing right over here. And what exactly is going to happen is that as theta rotates past 2 pi over 3, all the way to pi, R is going to extend back out to the size of 1, but it's R equals -1. R is negative all through here. So we're going to end up over here at this polar point, which is -1 comma pi. It's the point 1 comma pi, which is over here, reflected through the origin. So we create a loop looking like this. And now if you look at this graph, it's symmetric, right? We have a symmetry like that. And so I can expect that the rest of this curve will be generated symmetrically to the first part here. And that's indeed true. As theta marches past pi towards 4 pi over 3, so normally I would be drawing like, here's 4 pi over 3, I'd normally be drawing like in here. Instead, I'll be drawing in the reflected portion over here, which is going to give me this. And by the time I get to 4 pi over 3, which is this angle down here, R's come all the way back into 0. So the symmetry of this graph is going to correspond to a different symmetry down here, but it will still be asymmetry. And so now this guy comes in tangent to the 4 pi over 3 ray. And thankfully, as theta comes past 4 pi over 3, R is positive again and increasing. As theta comes past 4 pi over 3, R starts increasing really quick. By the time we're at 3 pi over 2, he's all the way out to 1. So here's the polar point, 1 comma 3 pi over 2. And we create this. Oh, tell me this pen isn't dying. And you can see what's going to happen then as I continue to let theta rotate, as my arm continues to walk around past 3 pi over 2 here. My little dude, this dot, is going to start running back out along that arm and connect with this guy, creating the missing symmetric piece of this. It's called a limison, something like that. So it's like one of the cardioid graphs, but with a little loop on the inside. So this is called a limison, and there's a little on the C. So one question you may be asking at this point, if you compare the two equations, R equals 2 plus 2 cos theta and R equals 1 plus 2 cos theta, what is it about this second equation that makes it different than this first equation? Why does this guy have a loop when this guy was just the heart, just the cardioid? And the answer comes from looking at the rectangular coordinate graph. This guy's rectangular coordinate graph spends some time below the horizontal axis. R is sometimes negative there. Whereas in the other fellow, R was able to come down to touch the horizontal axis, but never actually went negative. So the family of curves R equals, book do this? I want to use the same notation as they do. Yeah, A plus B cos theta call that R1, and R2 equals A plus B sine theta. These will generate either cardioids or limosons, depending on the size of the relative sizes of A and B. So these are graphs which are cardioids or limosons if A is larger than B, really greater than or equal to B, cardioid. And if A is less than or A is strictly less than B, then you'll get a limoson with that little loop. Okay. Questions about this graph? How we went from, well, how we got the rectangular graph, how we passed from the rectangular graph to the polar graph, or how we're classifying these things? Any questions about that at all? Chill the brightness a little bit on this. I feel like it's getting washed out. Everything feels pretty good? So you could, if you wanted to, you could go back and add this information to our little discussion of families of polar curves at the start, right? If you wanted to add the limosons and cardioids as the third family here, I think that would be totally appropriate to do. Some people I know also like to make flashcards for these. Just like when you're learning to memorize the shapes of graphs of power functions in college algebra, a lot of people end up making flashcards. When you're learning to memorize the shapes of polar curves, it's common enough to make flashcards. So the next kind of family I want to look at in a little bit more detail are those petal graphs. So we saw cos 2 theta last time. Cos 2 theta produced a petal graph that had 4 petals on it. Today I'd like to start by looking at the example sine 3 theta, and we'll compare that to cos 2 theta and see if we can come up with something similar to what we just saw. Okay. So we're going to here sketch r equals sine of 3 theta. Let's do that. I'm going to begin with a, where's it? There it is. I'm going to begin with the rectangular coordinate graph. And even though this guy's period isn't 2 pi, I'm going to still graph him all the way out to 2 pi to make sure I'm able to see what happens as my arm swings all the way around. This is a sine wave with amplitude 1, so I'll mark up here as +1 and down here as -1. Maybe it should be a little bit lower. If that's 2 pi, then this is pi. And what is the actual period of this? It's 2 pi over 3, right? It's a little bit odd. So one way to think of this is, instead of saying that the period is 2 pi over 3, we can talk about how many cycles we will go through between 0 and 2 pi. So regular sine goes through one cycle from 0 to 2 pi. Sine 3 theta will go through 3 cycles from 0 to 2 pi. So if that's half, I'm going to call this 1 pi over 3, 2 pi over 3, 1 pi over 3, about like that. So I'm going to mark off multiples of pi over 3. That's 3 pi over 3. This will be 4 pi over 3. There's a little bit off. 4 pi over 3, and then 5 pi over 3. And then 6 pi over 3 is 2 pi. So this is going to go through one complete cycle by the time I get to 2 pi over 3. The period is always 2 pi divided by whatever that constant is. So then here's going to be the end of one complete cycle. Here's going to be the start of one complete cycle. It might also be useful to find out the first time this guy is equal to 0. You'll find that it's at pi over 3. It's halfway through one of those cycles. So at pi over 6, we'll be up here at a max. And exactly halfway between here, we'll be down here at a min. So here's one full cycle of this wave. Come on, come on. All right, that's pretty good. These don't have to be perfect. And then I look at the next interval of length, 2 pi over 3. That's going to get me to, let's see, 1 pi over 3, 2 pi over 3, 3 pi over 3. Oh, it's going to get me to here. So we're going to come all the way up, back through here, all the way down, and back to here. I didn't mark things out perfectly evenly on my horizontal axis, so this is going to look a little bit squished, but you can see what's going on. And then over my next interval of length, pi over 3, we go through one more full cycle. Okay. So here's the graph of sine 3 theta from 0 to 2 pi. And just like on my cosine graph, I want to identify all those important points. I want to know anytime I go through equilibrium, anytime I hit a max, anytime I hit a min. This first max, so the period is 2 pi over 3, which means a half period is 1 pi over 3, so that's this x-intercept. So what does that make the the theta coordinate, the horizontal coordinate of that first max? It has to be halfway between 0 and pi over 3, so that has to be pi over 6. And then we have pi over 3 comma 0, and then down here, pi over 6 past pi over 3. What is that? Might be easier to think in terms of degrees. Pi over 3, that's 60 degrees. Pi over 6, that's 30 degrees. So this is going to be 90 degrees, pi over 2. Now this next guy, come past 2 pi over 3. Now we walk another pi over 6 past that. Where is that going to put me? If you prefer to write things out, I could say that this guy is going to be 2 pi over 3 plus pi over 6, right? Every one of these steps here is of length pi over 6. So that's 4 pi plus 1 pi over 6 is 5 pi over 6. And then we come through pi. We come one more pi over 6 past pi. That's going to be 7 pi over 6. Come a -1. Then we go through 4 pi over 3. This will be 9 pi over 6, which we wouldn't write like that, right? We'd write that as 3 pi over 2, sorry. And then we go through 5 pi over 3, which is 10 pi over 6 to 11 pi over 6. So all of this is stuff that we should be pretty comfy with. We haven't been sketching lots and lots of sine and cosine waves lately, but we did do lots and lots of this not too long ago. So if you need to brush up on that, by all means, brush up on it. If you'd like help, send me a message on Canvas or something, and I'd be happy to send you some review resources. So my next move is going to be to transfer this rectangular graph over into polar coordinates. There's a lot of symmetry here, right? The whole thing is symmetric about this, and then each piece is symmetric about its center. So probably after we sketch a little bit of this, we'll be able to see what's going to happen to the rest. Just like cos 2 theta was a petal graph, sine 3 theta I expect also to be a petal graph. The equation is very similar. Right now, I'm wishing I had some of that polar graphing paper. That stuff would be really nice here. But that's okay, we'll make do. When theta is 0, r is also 0. So we're starting here at the origin, and I'm thinking of my little arm as being pointing out like this right now. And as this arm begins to rotate, my point is going to start to walk out along it, which is going to sketch something that looks a bit like one of those petals. And by the time I get to theta equals pi over 6, my arm, my little guy, will already be at his maximum length out there on the arm. He'll be all the way out to r equals 1. So since r never gets larger than 1, I'm going to go ahead and mark that as like right here. Pi over 6, 30 degrees, something like this. So if I rotate this guy up by 30 degrees, he'll be something like right here. And this is the polar point, 1 comma pi over 6. And what happens, so as the arm rotates, the little dude runs out along the arm, drawing as he goes. That's going to create a little curved segment that looks like this. Now once theta has arrived at pi over 6, the arm still spins, it keeps spinning past this. The little guy is going to start running back in. So as I rotate past this, he's going to start running back towards the origin because r is decreasing as theta goes from pi over 6 to pi over 3. And by the time I get to pi over 3, he will have come all the way back into the origin. So that's going to create something that looks like this. And we're going to come in tangent to pi over 3. So maybe it should be a little bit higher like that. Something like this. Forgive the art. Now things get tricky because as r rotates past pi over 3, right, past pi over 3, I'm no longer going to be drawing up here where you would think from pi over 3 to pi over 2. Normally that has me drawing stuff up here. But r is negative now. So instead I'll be drawing in the reflected area, which is down here. But the same sort of thing happens. As theta comes past pi over 3 towards pi over 2, r is getting larger in size. this is decreasing, but r is no longer 0. So the absolute value of r is getting larger, which is going to have me run out until I reach this extreme point at pi over 2. So here's the polar point, pi over 2 comma -1. And we're going to draw something looking like this as we get out towards him. Now, as theta comes past pi over 2 towards 2 pi over 3, normally I would be drawing in this region, right, up here. But because r is negative, I'll be drawing in the reflected region down here. And what's happening is that r is shrinking back towards 0. So by the time I get to 2 pi over 3, by the time I'm working along this ray, or in actual fact, the reflected version, this ray, r will have contracted all the way back to 0. So that will create something that looks like this. Now from 2 pi over 3 to 5 pi over 6, r is positive again. So we're going to poke back out of the origin here at 2 pi over 3. And we're going to come out to this extreme point of 1 comma 5 pi over 6. So something like this. And then as we rotate past 5 pi over 6 towards pi, by the time we're along the pi ray, we should be back at 0. So we come in tangent to the horizontal axis like that. And yeah, we get a petal looking something like this. So this extreme point out here is 1 comma 5 pi over 6 in polar coordinates. Now something funny happens. So we just got to this point. As theta rotates past pi towards 7 pi over 6, normally I would be drawing in this region. And you might think that I'm going to get another petal over here. But because r is negative, I'm actually drawing in this reflected region again. So instead of getting a new petal, I'm just going to trace this petal again. And then as we rotate past 7 pi over 6 towards 4 pi over 3 down here, we come back into the origin. Rotating past 4 pi over 3 towards 3 pi over 2, r is positive again, which means I'm not going to reflect, and I'm just going to draw this thing again. And you can tell what's going to happen here. Everything to the left of this dotted line is going to create this image that we already saw. Everything to the right of this dotted line is just going to trace over that image again. So while cos 2 theta had 4 petals, sine 3 theta has 3. So the pattern or relationship that we might think we're observing there is a little bit more subtle. So as theta runs all the way out to 2 pi, we trace this whole thing again. Right? That's the take-home message. And the result is a petal graph with 3 petals rather than a petal graph with 6 petals, as we might have expected. And a very fair question would be why? Why the hell did this happen? And is it something about the 2 changing to a 3? Or is it something about the cosine changing to a sine? I will spoil it for you. The way that this works out is that if you have the family of curves, R1 maybe is cosine of n theta, or R2 is, and we could have a number out here, A, or A sine n theta. These will always be petal graphs. Petal or rose graphs of, you could maybe call this amplitude or max radius. A. And number of petals follows this rule. If n is odd, then you'll have n petals. So the family of curves A cos n theta or A sine n theta will always be a petal graph. The max radius or whatever, the max distance you get out from the origin is always that number A. But the tricky part is the number of petals. So if n is odd, then you'll have n petals. If n is even, then you end up with 2n petals. And it has to do with the way the natural period of the sine and cosine function divide. 2 pi, if you look at a function like cos 2 theta, or sine 4 theta, or cos 6 theta, or sine 10 theta, the period 2 pi can be chopped up nicely by even integers, chopped up nicely into regions that correspond to geometric space in the polar coordinate system. But if you have an odd coefficient here, if you have an odd number n, then the period of that function doesn't correspond to nice, clean geometric regions in the polar coordinate space. And so you end up with this kind of phase thing where instead of getting 6 petals, as one might intuitively expect from the first few examples you look at, if n is odd, because of the way things line up, you actually end up just with n petals. And if n is even, because the way things, I guess, maybe you could think of it as being a not lining up in the other case. I guess that's really maybe the better way to say it. You end up with 2n petals. And then the sine or the cosine determines the orientation. A cosine petal graph will always start at a max along the polar axis, and a sine petal graph will always start at the origin and come out to that first max somewhere else. So now we have our 4th family of polar curves that we understand pretty well. Any questions about these 2 more recent examples? These are a little bit more complicated than other stuff that we've done. Yes, sir. Oh, here, I think I might have to unmute you. Yeah, what's up?
Do you hear me?
I can hear you now.
How are you?
Hey, I'm good. I'm good.
Okay, so can you explain me the second graph of the polar graph? I don't catch up how to realize it. So.
Could you just say that one more time? I didn't quite follow you.
Yeah, I said, can you explain me the second graph, the polar graph? Yeah. How you make how you sketch it?
Maybe looking at a somewhat simpler example would be useful. So I'm doing the same thing that I did for all the other polar graphs. I'm starting with my rectangular graph, and then each of these important points are corresponding to points that I label on the polar graph. And I think about whether r is increasing or decreasing, and whether r is positive or negative as theta rotates around to draw the curve. So it's not a simple thing. I'm not going to pretend like it is, but maybe looking at a slightly simpler example, and there's one other kind of toy example I wanted to play with today, will be helpful. I am going to get some more papers because this is like bleeding through a little bit. So I will be right back, and we will look at one more example that I think will help.
Okay, thank you.
I gotta finish teaching. Okay. So one example that kind of helped me tie these ideas together for myself when I was learning them is the one I'm going to show you now. It's going to be the polar graph, not involving any trig functions this time, just of r equals theta. And we can run through the same process that we were for those other more complicated guys. And that might help understanding the process if that's been difficult. So first, we draw the rectangular graph. And this is not going to be a sine wave or anything like that. If this is the r-axis and this is the theta axis, then in regular rectangular coordinates, r equals theta, that's the same as like y equals x. It's a line. So this point right here might be 1, 1. This point right here might be pi over 2, pi over 2. And of course, over here, it would extend in the same way. So this is the rectangular graph. Now, normally I only draw these on the interval 0 to 2 pi, but this one is simple enough that I'm not even going to bother sketching it all the way out to 2 pi. Nor am I going to worry about negative theta values. So that's the rectangular graph, and from that, I can get the polar graph. Which is a little bit interesting. When theta is 0, r is 0. So we do start here at the origin. But then as theta increases a little bit, r increases a little bit. So if I look just a little bit later, I rotate up just a tiny bit from theta equals 0 to maybe theta equals pi over 6, then r will be pi over 6, which is, about 1/2. So if I mark this as like unit length, as length 1, then at 30 degrees will be right here at the polar point pi over 6, comma, pi over 6. And I'm writing those labels real small because I know it's going to happen. As theta then continues to increase from pi over 6 to pi over 4, r will continue to increase. So pi over 4, comma, pi over 4, pi over 3, comma, pi over 3, pi over 2, comma, pi over 2. Every time we go around, we go out a little bit further. This is going to generate what's called an Archimedean spiral. Oof. Right, this is the Archimedean spiral, r equals theta. This point right here is the polar coordinate point, pi over 2, comma, pi over 2. So r, the radius there, is pi over 2, and theta, the angle there, is also pi over 2. This would be the polar point, pi, comma, pi, because r is pi and theta is pi. This would be the polar point, 3 pi over 2, comma, 3 pi over 2. This would be the polar point 2 pi, comma, 2 pi. So I don't know if that's helping with the analogy or not. I hope that it is. But for the most part, you think of these graphs the same way you think of these rectangular graphs, the same way you think of a table of values, right? Really, this graph is the same information as a table of values with a little bit more information thrown in. The points that I have labeled here, I could have put that into a table. I could have just started with the table rather than starting with the picture and then drawn this graph, the polar graph, from the table of polar values. But having the picture, having the rectangular graph's picture also lets me think about, oh, is r increasing? Is r decreasing? Where does r become negative? So I know to reflect. All of those kind of subtle things. We can do maybe one more example with the petal graphs, if those are still feeling especially weird. Yeah, we have time. Let's do one last petal graph. What do we do? We did cos 2 theta, sine 3 theta. Let's do sine 4 theta. That's going to be gnarly. We haven't done sine 2 theta yet. Let's do sine 2 theta. So first I draw the rectangular graph. This is my theta axis. This is my r axis. Sine 2 theta is a sine wave of amplitude 1 and period pi. I will run through 2 full cycles. Over the interval 0 to 2 pi. So there's one cycle. And the next full cycle will look like this. Hamlet, be good, Bubba. Okay, so there's our normal graph, normal rectangular graph. This guy is halfway between 0 and pi over 2. That's pi over 4, comma 1. This guy is halfway between 3 pi over 2, or sorry, between pi over 2 and pi. So that's 3 pi over 4, comma negative 1. This guy halfway between pi and 3 pi over 2. Let's see, is 5 pi over 4, comma 1. And then this guy halfway between 3 pi over 2 and 2 pi is 7 pi over 4, comma negative 1. And so I could think of this as a table of values. I could think of this as a theta r table, which is how we graphed our first few polar curves, right? It's got 0, 0, pi over 4, 1, pi over 2, 0, 3 pi over 4, negative 1, and I could keep going, right, listing all the points here, here. But it's nicer to have it organized like this because this also gives you information about like rate of change, increasing, decreasing. It gives you a better feel for it than the table. So think of this as having the same value as the table, plus a little bit of added value, giving you a kind of visual representation. And then we can transfer the rectangular coordinate graph over into a polar graph. If you wanted to, you could just start plotting the points from this table in polar coordinates. So we start when theta is 0, r is 0. And when theta is pi over 4, r is 1. So here's the polar point, 1 comma pi over 4. Remember, we always list r first. But I want to know what the curve looks like in between there. And so the trick is to imagine this arm rotating, and as it rotates, imagine a little guy or a little dot or whatever running out along that arm, because that's what's happening. R is increasing. R is the distance this guy has walked out along that arm. R is increasing from 0 to 1 as theta rotates from theta equals 0 radians to theta equals pi over 4 radians. So I draw that. So this first little part of this rectangular graph corresponds to this first little part of this polar graph. Because as theta rotates from 0 up to pi over 4, r gets larger and it goes out to a max of 1. So here's theta equals 0, r equals 0. Here's maybe theta equals pi over 12, and r is small. And by the time I get out here to pi over 4, r is all the way out to 1. Now, as theta continues to rotate from pi over 4 towards pi over 2, r comes back into 0. So I imagine that arm rotating from here to here. And what happens as that arm rotates from here to here is my dot starts coming in. So if you follow the path that my finger just made, if you trace the path that my finger just made, it would look like this. And so that's what the polar graph looks like. Now as theta rotates past pi over 2 towards 3 pi over 4 over here, what's happening? R is no longer 0, so we're not going to be at the origin, but it is negative now. So instead of drawing in this region here, where I normally would, from pi over 2 to 3 pi over 4, I'll be drawing in the reflected region down here. What exactly is happening? Well, r is going to come out to this max of 3 pi over 4, negative 1 at 3 pi over 4. So the 3 pi over 4 ray is this guy, and the polar point, negative 1 comma 3 pi over 4, sits right here. So definitely it's necessary to practice plotting points in polar coordinates and to get very comfortable with the notation of polar coordinates before you can do this. if r was positive, but doing that same thing, I would draw a very similar looking arc over here as to what I had over here. But since r is negative, that arc will be reflected through the origin, giving me something that looks like this. And then as theta rotates past 3 pi over 4 towards pi, normally I would be drawing over here. The reflected space there is over here. And the curve that I will be drawing, is going to look like this. As theta comes past pi, r is positive again. So as theta rotates past pi, as my arm starts rotating through this range, r is positive, so I'll be drawing where you'd expect to draw again, no weird reflect through the origin bullshit. And I come out to a maximum r value of 1 when theta is 5 pi over 4. So 5 pi over 4 is here, 5 pi over 4 and 1, somewhere right around there. This is the polar point 1 comma 5 pi over 4. And the portion of the curve looks something like that.
How did you pick the quadrant for that?
Well, I'm just thinking about the theta values. So here theta is running from, I'm looking at theta going from pi to 5 pi over 4, right? I'm looking at this part of the curve where theta goes from pi to 5 pi over 4. Theta equals pi is this. Theta equals 5 pi over 4 is this. So I know I'm drawing in the first half of quadrant 3. Right, here's the line theta equals pi, and here's the line theta equals 5 pi over 4. So as theta runs from pi to 5 pi over 4, I expect to be drawing in this region. And because r is positive for those values of theta, I am actually drawing in that region. Had r been negative, I would have to reflect through the origin, but it wasn't negative. Does that make sense?
Yes.
I won't pretend like this stuff is super intuitive or super easy. I know that's not the case. So as those little questions come up, please ask them. I really appreciate you guys asking questions. Yeah. You can hold the space bar to unmute yourself if you want to talk, or I can unmute you, either one. Okay, there's a question?
Okay, so you said that we have to consider the positive position and negative position. So from pi to 5, can we lead a little bit down with it? Okay, from pi to 5 pi over 4, it increased. So
Yeah.
that is increased. The curve should be on the top, I think so.
So I know I'm going to go from this point right here, whose theta value is pi and whose radius is 0, to this point over here, whose theta value is 5 pi over 4 and whose radius is 1. Because here, theta is pi and r is 0, and here theta is 5 pi over 4 and r is 1. And so the question is just, what is the shape of this curve? I know I have to connect this point to this point, and the trick is to think about just rotating through at a constant speed and imagining the little guy running in and out along that rotating arm. So as this arm rotates through, here's 0 comma pi, right? Theta is pi and r is 0. I rotate just a teeny little bit past that, and r should be a little bit positive now. And I rotate a little bit past that, and r should be a little bit more positive. And I rotate a little bit past that, and r should be a little bit more positive. And finally, when I get to 5 pi over 4, r should be 1.
Okay.
Right? It's not, I know it's not super easy stuff. watch this, and when I post this recording, rewatch it and go through it and try working it on your own. Also, look at the stuff I've posted to the modules in Canvas. Those Patrick JMT videos are really good. And he does lots of examples like this.
Okay, thank you.
Of course. So as we keep going past theta equals 5 pi over 4 towards 3 pi over 2, which would have me down here, because this is theta equals 3 pi over 2, r needs to contract back into 0. So we'll draw something that looks like that. And then as we rotate from 3 pi over 2 to 2 pi, normally I would be drawing down here in quadrant 4, because that's those theta values, right? This is theta equals 3 pi over 2. This is theta equals 2 pi. So normally I would be drawing down here. But because r is negative, I'll be drawing that same sort of thing, just reflected through the origin. In other words, I take this petal right here and reflect it all through the origin. And that will be the end of my graph. Now this polar point is -1, 7 pi over 4. And a good check to see how comfy you are with this stuff is to look at this graph and make sure that these points labels all make sense to you. This one, I feel, should make good sense to everybody. We've rotated theta equals pi over 4 and walked out 1. This guy, though, is a little bit weird because this doesn't look like I rotated 3 pi over 4 and walked out 1. I rotated 3 pi over 4 to get to quadrant 4. That's not usually how we think of it, right? 3 pi over 4 I usually think of as a quadrant 2 angle. But oh, the radius is negative. So think about these guys first. Try to get comfy with these guys first. And then once you're comfy with those guys, try to think about these guys. If you haven't started on the polar coordinate homework, then this is going to feel very, very hard right now. And that's okay. But once you get through a meaningful chunk of that polar coordinate homework where you have to plot polar points that have positive and negative radii, and if you really spend the time thinking about what the negative radius does to the location of the point in the plane, then I do believe that you will get comfy with this. It's just going to be a matter of practice, and it's probably going to take quite a lot of practice, maybe even a little bit more than some of the other topics we've been playing with, because this is fairly abstract. It's a new way of thinking. Okay. Any other questions or comments or anything I could say to be helpful here? I do have one other thing to share with you guys. And I will see. You can see what I'm Googling here, polar Desmos. So, oh, I might have to select the specific share. Yeah. So if you Google, so the only way to get a limison graph is if it's negative in the rectangular coordinates. If you have a, that's true, but it's not an if and only if. Yeah, it's possible to get limisons, or it's impossible to get a limison in polar coordinates without the rectangular coordinate graph dipping below the x-axis or below the theta axis. You won't actually have a little loop. Some people refer to the cardioid shape also as being a limison, but that's not actually correct verbiage. So yeah, in order to get that little inside loop, you do need to have a negative value, negative r values. So the other thing I wanted to share with you guys here is Desmos' amazing ability to play around with polar coordinates. So you can look at some graphs of different functions. Let me change. Oh wait, no, this was just meant to be a part of the polar axis. Yeah, okay, polar grid. So here this red curve is r equals 3 minus 3 cos theta. We've looked at things like r equals 3 plus 3 cos theta, and so you can fiddle around and see what changing one thing to another does. If I make this a 2, then I'll introduce a little loop there because a is smaller than b. If I make this a 4, then that loop will come out to a little dimple. It won't even come into a sharp peak like it does on the first cardioid we looked at. If you just look at r equals 3 cos theta, you'll get a circle centered where we said it should be at 3/2 and of radius 3/2. So I invite you guys to play around with some of the things that the graphing software like Desmos can be useful for. In particular, I wanted to look at one of the things that was asked last time. What does the tangent function look like in this setting? Well, here's what the tangent function looks like in this setting. I had never graphed it myself. I do not know the name of that shape, but it's pretty damn cool, right? So make sure you practice drawing these graphs by hand. Especially as you work through the homework, it's important that you get comfortable drawing these polar graphs by hand, because there will be questions on the final exam where I ask you to do something like that. And even if we do it online, you will still have to scan and upload your work, just like I asked you to do for exam 3. So it's very important that you practice that, but also experiment, be brave and play around with different things in Desmos or wherever you feel comfortable playing around with things. But yeah, play with some graphing utilities, look at lots of examples. And then when it comes to the problems in the homework, please make sure to work them by hand, not just in the calculator or in Desmos. We are still going to have a 4th test. It will probably be something take-homey, project-y, something like that, something a little lower stress than the timed WebAssign test. But I haven't designed it, haven't even started to climb that hill yet. So yes, there will be exam 4. I have to stick to the syllabus, that's only fair. But it will probably be something a little bit less stressful than the way we ran exam 3. And I'll be sure to talk to you guys about it when we get closer. Any other questions or comments? Yeah, of course. All right, then that's where we're going to leave it for today. Please continue working on the WebAssign homework. If you need more time for anything, don't be shy about asking. I did clear out all the messages and submission extension requests, so everybody should be good to go. But as those things come up, don't be afraid to ask for help or more time on anything. All righty. Okay, then I will.
Thank you.
See you tomorrow. Yeah, thank you.